quantum is always mysterious to us. And even though we say a lot of things from outside, that we understand the basics of quantum mechanics, basically, many of us don't. The reason is the contradictory principles. And today I'm going to clarify for the kids who want to understand and then realize quantum mechanics in the most scientific way possible. First thing that you have to remember about quantum mechanics is that it has nothing to do with reality. So there is something mysterious, some mysterious unknown universe which contributes to the system. But one thing you have to remember very, very well. Quantum mechanics, though it says that tunneling means at one point the particle would disappear or system would disappear and reappear at other place, there is always a path involved for a quantum system evolution. So going from one place to another should not be mixed with the evolution of a system. So when the temporal evolution of a system happens, then a system crosses a path and then comes back to the initial state. If the loop is not complete, there is no transformation. So quantum, a system with time, means there will be a loop, a closed path. That you have to keep it in your mind. Even if it is written in the textbook or not, doesn't matter, because it will help you to understand that when the system traverses a path and comes back, then it acquires a phase depending on the path or the loop. There are several cases, gauge potentials, and many examples where you find explicit application of this particular concept, that it comes back and acquires a phase. You can say that Pancharatnam was the first person in 1955 to say like this. So coming back and complete a path, you get something, but where you get this? You get this from hyperspace, not higher dimension, hyperdimension, not some non-linear effect. No linear effect, no non-linear effect, no real effect, no higher dimension, hyperdimension. Length, pitch, area, volume, these are real dimensions. You can really feel them. Even in quantum mechanics, when different qubits are radially oriented in different directions, that radial orientation concept is absolutely classical. So when you say that I want to build a 360 qubit quantum computer, that means 360 by 360 is equal to 1 degree. So 1 degree solid angle, you have to have radial vectors oriented around it, and then you have to add the correlation function. So orientation with classical is important. Listen to this very, very carefully. Classical orthogonality is a must. Classically, the condition that you need for quantum system for realizing a quantum system, that is a must. That is a preliminary basic criteria that you have to meet. For an example, many people don't understand the difference between orthogonal and unitary. So orthogonal is O dagger O is equal to identity. Okay. So like real valued, and could be say length and angles. Real vectors are kind of preserved. But when you go to quantum, you find U dagger U is equal to I. So basically inner product or probability amplitudes, and the dynamics is reversible dynamics, not in the real space but in the Hilbert space. Hilbert space means imaginary phase spheres where all possible values are there, astronomical number of values are there. So if you think you want to create a say unitary transformation or unitary system, or a tensor which is a system that is following the unitarity, then if you think that it will not be orthogonal, then that's a stupidity. So if you go from analog of a system from classical to quantum, that particular preservation is a must. In addition to that, you will have correlation and other kind of preservations that you have to maintain. So quantum means you go to the hyperspace that is imaginary, that has nothing to do with linearity, non-linearity, log space, anything that is real. Higher dimensions, all the concepts are real, nothing. Hyper dimension, that means AI. Iota, I square equal to -1. Why I is so, quantum mechanics people, why they love it? Because I square equal to -1. That means imaginary square is equal to plus. So if you have a x-axis reality and y-axis imaginary, then you can cross and come back to the -1. So I square -1. So this is why I is simply a tool. It is not given by the universe that okay, I am giving you I, and from today onwards I will show you the path towards the quantum. No, 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 no. I is simply a tool we have imagined for the sake of our purpose to take a value from hyperspace whenever there is a evolution of the system. A system point moves through a path and comes back and acquires a geometric phase depending as a function of the path, because dynamic phase doesn't depend on the path, it just is a function of time. So when you have this path dependence and you get the value, then it is quantum. So where you are getting this value, if you say you are getting it because you move through the path, then you are making a blunder. So see these difference. You are saying, we are teaching the kid that look, if you pass through the path and you come here, because of the function of the path, you are acquiring a phase, and this phase is a geometric phase because it is a function of the path, because I am taking a path integral. Then always remember, this path is not a real path where you walk. I repeat, this path is not in the real space. It is in the imaginary phase spheres where the motion happens and it comes back over there. You can consider something like this. You have a sphere and you make a hole on it, and that's a singularity region, and you embed a small sphere over there. Now this sphere, the guest sphere and the host sphere, they can interact by the host sphere projects from imaginary space IH cut something to the guest, and the guest projects something to the host by IH cut. So that is how they communicate with each other. And when I'm saying that it comes by a path and then reaches the initial position, then what is happening is you are moving through that hyperspace, that embedded sphere. You are going there, taking the turn, and you're coming back. So that is a kind of thing. Then there is some people say, oh, it is not, they don't commute, they're not commuting. What is that? If there are A and B, two variables, position and momentum, and you are able to measure position, and after that you measure momentum, it's fine. There you do it 100 times, they give the same value. But if something happens that you measure the position and then you measure the momentum, and you find that because you measure the position, momentum has changed, and therefore if you measure the momentum, position has changed, then ordering of measurement affects, then you say that they are not commuting, they are quantum. Here nobody explains to you one very interesting feature. That is, when you are measuring first A and then B, because of A, B is changed, we could stop over there. And we could say in classical, you measure A and after that you measure B. B, if you knew the earlier the values, B's value has not, doesn't change because of measurement of A. Or we could say you measure B and then A is changed. That is because you measured momentum and now you are measuring position. First you measure position and then momentum. Either of the case is quantum. No. This is important. If you want to understand quantum mechanics, learn this particular feature very, very well. It's not written in the book. That's why I'm saying. So when they say that I measure A and then I measure B, uh, and if I measure B first and then measure A, then there is they are different. That is important. That's where the reality breaks down. Otherwise, if I measure A and that changes B, or I measure B that changes A, that this event is classical. You can explain it with coupling. But when you measure A and then B and measure B and A, that means a real function cannot predict what is happening. Earlier when I explained quantum mechanics, I said 10 variables are there, and if I change one of them, 9 of them changes in a different way, and I can choose any of the 10, and the rest of the 9s will change in a different way. Then a real function cannot explain what is happening over there. There cannot be any logic, cannot be any algorithm, and that will ensure that there is quantum. So it's non-commute. What is meant? Commute means a b, a comma b, and then you put a third bracket and is equal to 0, something like that. You measure a and then measure b, you measure b. So ab minus ba is equal to 0, something like this. And in case of quantum, ab minus ba is what? AB minus BA is the contribution of the hyperspace that is over there in the imaginary world because of their relationship of projected hyperspace connected with the hyperspace or imaginary world. They pass through that imaginary world as if there is a sphere and then singularity and then there is another one. So you have to pass through that. Because you pass through that, an additional contribution comes. So it is not just measuring B after A and measuring A after B. It is the difference of those two measurements which is the effective contribution. So it means it is not about a physical coupling that if you measure one and then measure one A, it changes B, so you may do the measurement. No, it is that even if you do the measurement of B and then A, that non-linearity, that asymmetry is not important. Even if you neutralize asymmetry, even if you neutralize non-linearity, even if you neutralize all higher dimension to logarithmic space or a spatial contraction or whatever you do, unless until you have an undefined situation where you embed a hyperspace which can contribute to the reality, you cannot realize quantum. So what we learn today, we learn that quantum mechanics has something to do with an imaginary universe that is there, and system wants to evolve and has to return. Loop must be there, and otherwise you cannot find transformation. So transformation coming from the hyperspace, unless until that contribution of the hyperspace is measured, you can never say a system is quantum. So something has to come from the hyperspace, and then you have to root out all possibilities of three different things: linear coupling, non-linear coupling or logarithmic coupling, fractal coupling or whatever, and if you have a higher dimensional coupling. When you neutralize all possibilities one by one, and even after that you find that some contribution is still there, some correlation is still there, that is quantum. Now you can have Bell's inequality and many other kind of inequalities are there, all different protocols. You can even yourself, you can invent a new protocol. Nobody is stopping you. It is that how sincere you are. So we have created our own protocol to test quantum in a much more efficient and advanced way, so that they, I mean, in many cases, for an example, Wigner function, there should be a negative probability. There should always be a negative probability, negative features. Always negative is not right. So there are other things also. What other things? So no, quantum is very difficult. There are other things. This other thing means you just rule out all possible real relationship, linear, non-linear, fractal, yeah, logarithmic, or any real function, any higher dimensional transformations, any kind of transformations, any kind of invariance that you apply. Everything you do in the real term, in the real world, still there is an additional factor that is contributing, and when you get that, that is quantum. That's why in experiment proving that there is quantum can never be one experiment. It will be series of experiments. If one person does one experiment, no, two, three, four, and you have to say step by step, I have ruled out nonlinear interaction, I have ruled out linear coupling, I have ruled out logarithmic or space invariant relationship. Log plot means always space invariant relationship, or topological invariance, that kind of relationship, if it is over there. So that you have to go through. Then higher dimensional relationship, everything, when you neutralize and still you are getting it, then you say there could be quantum mechanical effect over there. So that is in the honest sense. Else you can just do a classical measurement. I hope that with this I have been able to make you clear what is quantum, and why it is mysterious, why it is difficult to prove something is quantum, and nearly impossible. And somebody can come up with some argument to prove that it is not truly quantum. So this is for the kids. I hope that young kids who are learning quantum mechanics have enjoyed this.